Why symmetry created everything? Let me tell you something that will change the way you see every single thing around you. The chair you're sitting in, the air you're breathing, and the screen you're staring at, the atoms in your bones, all of it, every particle, every force, every structure in the entire universe exists because something broke, not something small. And it's the most fundamental thing in all of physics, symmetry. And when it broke, it didn't just change the universe, it created it. And so I'm Leonard Susskind, and I've spent over 50 years studying the deepest laws of nature. Quantum mechanics, general relativity, string theory. And after all those decades, after all those equations, after all those arguments with the smartest people on the planet, I can tell you the single most important idea in all of physics. And so it's not energy, it's not matter, it's not even space or time, it's symmetry, and the fact that symmetry breaks. That's where everything comes from, everything. Let me show you what I mean. And I promise you, by the end of this, you will never look at reality the same way again. Start with something simple. Look at a perfect sphere, a billiard ball, a marble, whatever. Rotate it any way you want, it looks exactly the same. That's symmetry. The object is unchanged under a transformation, in this case, rotation. Now that might seem like a trivial observation, and who cares if a ball looks the same when you spin it? But here's the thing, in physics, symmetry isn't just about shapes looking pretty. Symmetry is the deepest organizing principle of the universe. Hence, it tells us what's possible and what's forbidden. It dictates the laws of physics themselves. In 1918, a mathematician named Emmy Noether proved what I consider the most beautiful theorem in all of physics. She showed that every continuous symmetry of nature corresponds to a conservation law. Hence, every single one, if the laws of physics don't change over time, if they're symmetric under time translation, then energy is conserved. Hence, if the laws don't change from place to place, if they're symmetric under spatial translation, then momentum is conserved. Hence, if the laws don't change when you rotate your coordinate system, then angular momentum is conserved. Think about what this means. Hence, the reason energy is conserved, the reason you can't create something from nothing, the reason perpetual motion machines are impossible is because of a symmetry. And the laws of physics are the same today as they were yesterday. That's it. That's where conservation of energy comes from, not from some mystical principle, from symmetry and momentum. And the reason a moving object keeps moving unless something stops it, Newton's first law, that comes from the fact that the laws of physics are the same here as they are over there. And space doesn't have a preferred location. That spatial symmetry gives you conservation of momentum. Noether's theorem is so profound that it still gives me chills after all these years. And every conservation law we know, every quantity that's preserved in every interaction, every rule that governs what can and can't happen in the universe, all of it traces back to a symmetry. But here's where things get really interesting and really strange. The universe, as we observe it, is not symmetric, not at all. Look around you. And matter exists, but antimatter is almost entirely absent. The electromagnetic force is completely different from the weak nuclear force, and particles have mass, but the equations that describe them work most beautifully when particles are massless. The universe is full of broken symmetries, and that's not a flaw. That's the point. Hence, because it turns out a perfectly symmetric universe would be the most boring thing imaginable. It would be nothing. Literally nothing. Let me explain why. Imagine the very early universe, hence, not the universe today with its galaxies and stars and planets and people. The universe as it was in the first fraction of a second after the Big Bang. And temperatures so high that your mind can't comprehend them. Trillions upon trillions of degrees at those temperatures. The universe was in a state of almost perfect symmetry. Hence all the fundamental forces, electromagnetism, the weak nuclear force, the strong nuclear force, were unified. They weren't separate forces. Hence, they were different aspects of a single symmetric interaction. All particles were massless. They all zipped around at the speed of light. There was no distinction between electrons and neutrinos. Hence, no distinction between quarks of different types. Everything was the same. Everything was symmetric. And if the universe had stayed that way, if that perfect symmetry had persisted, there would be no atoms, no molecules, no chemistry, no stars, no planets, no life, no you, and nothing but a featureless soup of identical massless particles flying around in perfect democratic equality, beautiful symmetric, and completely dead. Hence, the universe you live in, the universe with structure and complexity and beauty and terror and consciousness exists because that symmetry shattered. And the way it shattered is one of the most dramatic stories in all of science. Let me take you through it step by step. The first symmetry breaking happened at about 10 to the minus 36 seconds after the Big Bang. That's a decimal point followed by 35 zeros and then a 1. An incomprehensibly short time. And so at this moment, the temperature dropped just enough for something called the grand unified symmetry to break. Before this moment, 3 of the 4 fundamental forces were unified into a single force. And after this moment, the strong nuclear force, the force that holds quarks together inside protons and neutrons, separated from the electroweak force, it became its own thing. It's a distinct force with its own rules, its own strength, its own character. This wasn't a gentle transition, it was violent, catastrophically violent. And when this symmetry broke, it released an enormous amount of energy that drove a period of exponential expansion called inflation. The universe doubled in size every 10 to the minus 37 seconds. And in a tiny fraction of a second, a region smaller than a proton expanded to something larger than the observable universe today. And inflation is one of the most extraordinary ideas in cosmology, and it's driven by symmetry breaking. And the energy released when the grand unified symmetry shattered literally inflated the universe into existence as we know it. Without that symmetry breaking, no inflation. Hence, without inflation, no large-scale structure without large-scale structure, no galaxies. Without galaxies, no stars without stars, no heavy elements. Without heavy elements, no planets. Hence, without planets, no life without life. No one to wonder where it all came from. All because the symmetry broke at 10 to the minus 36 seconds. But we're just getting started. Hence, the next great symmetry breaking happened at about 10 to the minus 12 seconds. Still unimaginably early, but relatively late compared to the first one. This is when the electroweak symmetry broke. Hence, before this moment, the electromagnetic force and the weak nuclear force were unified. They were the same force described by the same equations operating with the same strength. Hence, photons and W and Z bosons were all the same kind of particle, all massless, all equivalent. Then something happened. It's a field that permeates all of space. A field that had been sitting in a symmetric state suddenly shifted. It fell into a new configuration, a lower energy state that was no longer symmetric. Hence, this field is what we now call the Higgs field. And this moment, this symmetry breaking event, is where mass comes from. Let me say that again because it's so important. It's mass. The thing that gives you weight, the thing that makes matter solid, the thing that keeps your feet on the ground, the thing that makes stars collapse under their own gravity, the thing that is responsible for the very existence of atoms and molecules and everything built from them, mass comes from a broken symmetry. Before the Higgs field shifted, all particles were massless, and they flew around at the speed of light with no resistance, no inertia, no weight. After the Higgs field shifted, some particles started interacting with this field. Hence, the more strongly they interacted, the more mass they acquired. Electrons got a little mass, quarks got more, the W and Z bosons got a lot, and photons. The particles of light didn't interact with the Higgs field at all. They remained massless. That's why light travels at the speed of light. Hence, because photons never acquired mass from the Higgs field because the symmetry breaking treated them differently. This is what the discovery of the Higgs boson at CERN in 2012 confirmed. Hence, not just the existence of a new particle, but the mechanism by which symmetry breaking gives mass to everything in the universe. Hence, every kilogram of your body, every gram of matter in every star, every ounce of material in every planet, all of it is a consequence of a field that decided to break a symmetry about 10 to the minus 12 seconds after the beginning of time. Now let me tell you about the symmetry breaking that I find most mysterious and most disturbing, the one that determines why you exist at all. It's matter versus antimatter. The equations of particle physics are almost perfectly symmetric between matter and antimatter. Hence, for every particle, there's an antiparticle with the same mass but opposite charge, electrons and positrons, protons and antiprotons, quarks and antiquarks. And in the early universe, matter and antimatter were created in nearly equal amounts. And when matter meets antimatter, they annihilate each other. They convert completely into energy, photons, light. So here's the problem. If the universe started with equal amounts of matter and antimatter, and if they annihilate when they meet, then everything should have annihilated. Hence, every particle should have found its antiparticle and converted into light. The universe should be nothing but a bath of radiation. No atoms, no molecules, no stars, no you, no me, nothing. Hence, but that's not what happened. Hence, some tiny asymmetry, some slight breaking of the matter, antimatter symmetry, meant that for every billion antiparticles, there were 1,000,000,001 particles. And it's one extra particle for every billion. That's it. That tiny excess, that microscopic violation of perfect symmetry, is where all the matter in the universe comes from. Hence, everything you see, every galaxy, every star, every planet, every atom in your body is the leftover residue of that tiny asymmetry. You're a rounding error in the universe's bookkeeping. And say, 1 in a billion surplus from a broken symmetry that we still don't fully understand. We know the symmetry was broken. We can see the evidence the universe is made of matter, not antimatter. But we don't know exactly how it happened. There's a property in physics called CP symmetry, the combined symmetry of charge conjugation and parity. And if CP symmetry were perfect, matter and antimatter would behave identically in every situation. And for a long time, physicists assumed CP symmetry was exact. Then in 1964, James Cronin and Val Fitch discovered that CP symmetry is violated in the decays of certain particles called kaons. The violation is tiny, incredibly subtle, but it's real. And it opened the door to understanding why matter won the war against antimatter in the early universe. Although, honestly, we still don't have the full picture. The CP violation we've measured is not enough to explain the matter-antimatter asymmetry we observe. There must be additional sources of symmetry breaking that we haven't discovered yet. This is one of the biggest unsolved problems in all of physics. Why does anything exist rather than nothing? The answer is symmetry breaking, but we don't know all the details yet. Let me now tell you about something that connects all of this to the deepest questions in modern physics: gauge symmetry and the origin of forces. This is where symmetry goes from being a nice organizing principle to being the actual engine of reality. In the 1950s and 60s, physicists discovered something remarkable. The fundamental forces of nature, electromagnetism, the weak force, the strong force, are not just constrained by symmetries, they are created by symmetries. The technical term is gauge symmetry. And the idea goes like this. Imagine you have a field, say the electromagnetic field. There's a symmetry in the equations that describe charged particles. You can change the phase of the quantum wave function of a charged particle at every point in space by a different amount, and the physics doesn't change. But for that to work, for the equations to remain consistent under this local symmetry transformation, you need a new field. It's a field that compensates for the changes you're making to the wave function. That compensating field is the electromagnetic field, the photon. In other words, the photon exists because of a symmetry requirement. The electromagnetic force exists because the universe demands that a certain symmetry be maintained. Hence, if you remove the symmetry, you remove the force, no symmetry, no photons, no light, no electricity, no magnetism, no chemistry. The same logic applies to the other forces. Hence, the strong nuclear force arises from a gauge symmetry called SU3 color symmetry. Quarks come in 3 colors, red, green, and blue. Hence, these are just labels, but the symmetry between them, the requirement that the physics is unchanged when you rotate quarks in color space, demands the existence of 8 new particles, the gluons, the carriers of the strong force, the particles that hold protons and neutrons together, the particles that hold atomic nuclei together. Without that symmetry, no gluons, no nuclear force, no atomic nuclei, no atoms, no periodic table, no chemistry, no life. The weak nuclear force comes from another gauge symmetry, SU2. This symmetry combined with U1 gives us the electroweak interaction before symmetry breaking. Hence, after the Higgs mechanism breaks the electroweak symmetry, the W and Z bosons become massive. The photon stays massless, and the electromagnetic and weak forces go their separate ways. And so here's the picture. Every force in nature, every interaction between particles, every push and pull at the fundamental level is a consequence of a symmetry. The forces don't just obey symmetries. They are symmetries made manifest as fields and particles and interactions. This is what I find most breathtaking about modern physics. The universe, at its most fundamental level, is built from abstract mathematical symmetries. The stuff of reality, forces, particles, mass, energy, all of it is symmetry and symmetry breaking dressed up in physical clothing. Now, let me take you to an even deeper level. Because the story doesn't end with the standard model, it goes all the way down, or perhaps all the way up. In the framework I've worked on for much of my career, string theory, the fundamental objects are not particles at all. They're tiny vibrating strings of energy. And the different particles we observe, electrons, quarks, photons, all of them correspond to different vibrational modes of these strings, like different notes on a violin. And what determines which vibrational modes are possible? Symmetry, the symmetries of the extra dimensions in which the strings vibrate. And string theory requires either 10 or 11 dimensions of space-time, depending on the formulation. We see only 4, 3 of space and 1 of time. And the other 6 or 7 dimensions are compactified, curled up so small that we can't detect them directly. But the geometry of those extra dimensions, the way they're shaped, the symmetries they possess, determines everything about the physics we observe. The particle spectrum, the force strengths, the values of all the constants of nature, everything, and the string theory landscape, the vast space of possible compactifications that I helped develop, suggests that there are an astronomical number of possible geometries, and maybe 10 to the 500 different possible shapes for the extra dimensions. And each one gives a different universe with different symmetries and different symmetry-breaking patterns and therefore different physics. And so in most of those universes, the symmetries break in ways that don't produce anything interesting. No stable atoms, no complex chemistry, no possibility of life. We live in one of the rare universes where the symmetries broke in just the right way to produce complexity. Hence where the strong force is strong enough to hold nuclei together, but not so strong that it collapses them. Hence where the electromagnetic force is strong enough to hold atoms together, but not so strong that it prevents nuclear reactions in stars. Hence where the Higgs field gives particles masses that are in the right range for chemistry to work, where CP violation was just enough to produce a surplus of matter. Hence where the cosmological constant is small enough that the universe didn't fly apart before structures could form. All of this comes from how symmetries break. Every detail, every parameter, and every feature of reality that makes your existence possible. Now, let me tell you about a symmetry that might be the deepest of all, and one that's almost certainly broken, supersymmetry. Supersymmetry is a proposed symmetry between bosons, particles with integer spin like photons and gluons, and fermions, particles with half-integer spin like electrons and quarks. And if supersymmetry is exact, then every particle has a superpartner. Electrons have selectrons, quarks have squarks, photons have photinos, gluons have gluinos. And these superpartners would have the same mass as their partners. But we haven't found any superpartners. We've looked hard. Hence, the Large Hadron Collider at CERN has searched for superpartners for over a decade. Nothing, which means one of two things. Hence, either supersymmetry doesn't exist, which would be disappointing but possible, or supersymmetry exists but is broken. Hence, the superpartners exist, but they're much heavier than their partners because the symmetry that relates them has been broken at some high energy scale. Most theorists, including me, suspect the latter. And supersymmetry is too beautiful, too mathematically compelling, too useful for solving deep problems in physics to not be part of the story, but it must be broken. Hence, in the way it breaks, the mechanism and the energy scale of supersymmetry breaking would determine the masses of all the superpartners and potentially solve some of the deepest mysteries in physics, hence including the hierarchy problem. Why the Higgs boson mass is so much lighter than we'd naively expect. This is one of the biggest open questions in fundamental physics. And it's a question about symmetry breaking, like so many of the deepest questions. Here's something I want you to really sit with, because I think it's the most profound implication of everything I've told you. The universe didn't start with stuff and then organize it. Hence, the universe started with symmetry and then broke it. And the breaking is what created the stuff. Before symmetry breaking, there were no distinct forces, no massive particles, no atoms, no structure. And it's just a featureless, symmetric state. The complexity we see, the diversity, the richness, the beauty of the physical world, all of it is a consequence of imperfection, of broken symmetry. And so the universe failing to maintain its original perfect state. You exist because the universe is flawed, because perfection is sterile, hence because true democracy among particles and forces produces nothing but a boring, formless soup. It's the asymmetries, the imperfections, the broken symmetries that create everything interesting. Hence, everything beautiful, everything alive. This is true at every level. In particle physics, broken symmetries give us mass, forces, and matter. Hence, in chemistry, broken spatial symmetries give us molecules with definite shapes, left-handed and right-handed, that can perform specific functions. In biology, symmetry breaking is everywhere. Hence, your heart is on the left side, the DNA helix is right-handed, your brain is asymmetric with different functions in different hemispheres. Hence, all consequences of broken symmetries at the molecular level. Hence, in cosmology, the slight asymmetries in the cosmic microwave background, the tiny density fluctuations from the early universe amplified by gravity over billions of years, are what created galaxies and stars and planets. If the early universe had been perfectly smooth, perfectly symmetric, there would be no structure at all, no clumping, no galaxies, no stars. And it's nothing but a uniform expanding gas. We owe our existence to imperfection at every scale, from the quantum fluctuations of the Big Bang to the molecular asymmetries of DNA. And all of it traces back to the same principle, symmetry breaking. Now, could I be wrong about some of this? Of course, science is always provisional. And our understanding of symmetry breaking in the early universe is based on theoretical frameworks that haven't been fully tested. Hence, the details of the grand unified symmetry breaking, if it happened at all, are speculative. Supersymmetry might not exist. The string landscape might be wrong. But the core idea that symmetry and symmetry breaking are the organizing principles of the universe, that forces arise from gauge symmetries, that mass comes from the Higgs mechanism, that the matter, asymmetry comes from CP violation. These are experimentally confirmed facts. The standard model of particle physics, which is built entirely on symmetry principles, has been tested to extraordinary precision. It's one of the most successful theories in the history of science. Every prediction confirmed, every symmetry verified, every symmetry breaking pattern observed exactly as the theory demands. So when I say symmetry created everything, I'm not being poetic. So I'm not using a metaphor. I'm stating what the physics actually tells us. The universe is made of symmetry. And everything you see, everything you touch, everything you are, is what happens when that symmetry breaks. Let me leave you with this thought. There's a Japanese aesthetic concept called wabi-sabi. The beauty of imperfection, the idea that a cracked pot, an asymmetric garden, a weathered piece of wood is more beautiful than something perfect and pristine. I think the universe practices wabi-sabi at the deepest possible level. Its perfection, its original symmetric state, was sterile, empty, dead. It was the cracks, the breaks, the imperfections in that perfection that created everything worth caring about. Stars, planets, oceans, mountains, trees, animals, humans, consciousness, love, art, and science, all of it products of broken symmetry, products of a universe that couldn't maintain its own perfection. And thank goodness for that. Because perfection, it turns out, is the most boring thing in existence. It's the imperfections that make the universe alive. And after 50 years of studying the laws of nature, that's the deepest truth I've found. The universe is built on symmetry, but it lives on broken symmetry, and so do you. And think about that the next time you look in the mirror. Every asymmetry on your face, every irregularity in your body, every imperfection you've ever worried about, those aren't flaws. Those are the universe doing what it does best, breaking symmetry, creating something from nothing, building complexity from simplicity. You're a monument to broken symmetry. The most complex structure we know of in the entire cosmos, the human brain, exists because the universe refused to stay perfect. And that, to me, is the most beautiful fact in all of physics.